Record. Okay, class. So for the recording, just thought I would pull up the U.S. debt clock, give everybody a good grounding in our financial future here. Hope you guys enjoy paying this stuff off. Me heading into retirement, I hope I get to avoid a lot of that privilege. So at any rate, just Google National Debt Clock and you can pull this up today. Keeps rolling. Okay, let's see. What are we going to do today? We're going to finish this PTC 4.1 discussion. We're almost done. You know, we went over this, I have unstable internet. Well, it is Tennessee Tech. You can't expect too much. So we talked all around the control volume of this boiler steam generating unit. Find all this stuff last time. And so I wanted to spend a little time on this next. So let's go down at the bottom, look at the equations, and then we'll go up and look at all the different items. Let's see here. Okay, so just efficiency definitions. You know, we can do it with output divided by input, or we can do it input minus input. So he's doing some very simple algebra up here. Efficiency output over input times 100. And the output would be the input to the boiler minus losses. And then the input is defined as the, we'll say that's the energy and the fuel, coal or natural gas, plus any credits, and we'll see how those are calculated. And then he just does, he notices on the heat balance, is the chemical energy, say in the coal or the natural gas plus the credits, is equal to the output minus the losses. Or, you know, you can do some algebra and show all of this. So basically, we're just talking about the efficiency of the steam generating unit, but it's kind of interesting to see how they break all this stuff down to make these measurements and buried back and all that stuff that big boiler steam generator and took that up, and the equations are here to evaluate all of this stuff with explanations. So it's really a pretty complete document. But anyway, so you see the heat in the energy bound up in the coal. The ultimate analysis on fuel. But then anytime we have energy entering that control volume, that's, you know, that's deemed a credit. And so we can calculate all of these little credits, you know, to do our basically first law energy balance correctly. So there's heat in the entering air. So, you know, there isn't some energy content in the air that comes into that envelope, that boundary you see below. If we happen to be atomizing the fuel, we could be on fuel oil and require atomizing steam to break it up into the proper consistency for the burners to combust it. So if we're putting in atomizing steam, that's energy that goes into the control volume. Sensible heat in the fuel. So that fuel has, you know, if it's pulverized coal, at whatever condition it enters the boundary, it has some temperature. It's not absolute zero. So it carries in some sensible energy with it. Pulverizer or crusher power, that's usually an electric motor that's spinning. And so that that electric energy that makes the pulverizer spin is considered to be within the control volume. So that would need to be accounted for. If boiler circulating pump power, if we have a forced circulation, kind of pumping the feed water up through the water wall tubes instead of letting it happen by natural convection, then we would need to include that power. If it's natural convection, then you just won't have that piece. The primary air fan power is considered to be in. Recirculating gas fan power, if we're doing flue gas recirculation for NOx control, then the power to run that fan would be considered a credit. Heat supplied by moisture in the entering air. So any moisture we're bringing in, that's water vapor. And you know, water vapor, even in the atmosphere, is probably someplace around 1,000 BTUs a pound coming in. So that's energy into the control volume. And then if we have any cooling water, it has some temperature where it enters the control volume. So that would be heat coming into the control volume as well. So, you know, if you're doing a big boiler, you look down through all this stuff and you talk to the guys, you know, that run the boiler that know about it. And you say, well, you know, do we have all this stuff? And they say, well, we got a natural circulation boiler. Well, okay, then we get to cross off the B, capital B sub X, because we don't have that. Okay, well, that's good. You're going to have a primary air fan, that's for sure. Are you doing flue gas recirculation? You may not be doing that, so that could drop out. So, you know, you don't necessarily have all of these on every boiler, but it's certainly the possibility. And let me see, do I have a chat? I'm getting better at this. Hard to understand. Is it still hard to understand me? Hello? Nicholas?
It's become a lot easier to understand you now.
It may have been when we had that upset with the internet. It said I had unstable internet. Okay, good. Thank you. Don't hesitate to interrupt if something breaks down. Okay, so those are the credits. And then we see the primary flows crossing, you know, this would be the steam and the reheat and all that stuff. And so, again, we talked through all this, but I think it's a good summary. So what do we have? We got, you know, from our feed water heaters coming into the economizer, we've got heat in the feed water coming in. And of course, we can do a temperator spray. And also included in this injection is circulating pump injection water. Okay, so I'm thinking that I don't know if that is for cooling or whether it's for any sort of makeup. Usually the makeup water just goes directly in the drum. So I'm not sure. If you really wanted to know, you'd have to go back and look in the equations, and it will tell you exactly the algorithm by which that's calculated. The desuperheating water is the attemperator spray. I know that. And then we've got heat and blowdown. Okay, so we bring out blowdown, and that's to keep the level of impurities in the boiler water at the appropriate level so we don't get scaling. And then circulating pump leak off water. A lot of times those have packing, and packing glands leak and stuff like that. So understand that. That's energy leaving. Heat and steam for miscellaneous uses. We could be pulling steam off of this unit. Maybe we're pre-warming a turbine on a different unit, and they haven't fired that boiler yet, and so we can tap off some steam for other purposes. Maybe we're doing space heating inside the boiler house or something. So just for miscellaneous uses. And then we have our reheat coming out of the high pressure turbine, reheat steam coming back. We have additional temperature flows to control the amount of superheat and temperature leaving, and then the reheat steam flow back out to the intermediate pressure turbines. So you guys are just getting to be professionals on all this stuff. And then losses. Oh my goodness. Look at all of the losses. I think they count to 15. You can count them. I'm not going to count them again. I've counted them umpteen times. I think it's 15, but I could be remembering wrong. But anyway, it's a bunch, you know. So these are all different items that would be considered an energy loss from the system. And a lot of this we've talked about. We probably haven't talked about all of this, but it's a good summary. Unburned carbon in refuse. So that's the LOI, right? Loss on ignition. And that's the amount of, and you measure that by the amount of carbon in the ash. You know, you take some samples of ash, you send it off to the lab, and you say, well, how much carbon's in here? If I had perfect burnout, there would be no carbon, right? I'd burn it all into CO2, but you don't get all of it. Heat in dry gas, so that would be the dry flue gas. And so say they're gonna calculate the moisture losses separate from the dry flue gas losses. So that's heat in dry gas. So that flue gas is leaving that envelope pretty warm, and it's taking energy with it. Okay. Well, we know when we did some of the little combustion analysis, we saw that the coal had water, had moisture in it. And so that's probably liquid, in the liquid form, bound up in the coal particles, right? And so that's, as we burn that liquid water is going to vaporize, and then it's going to leave as vapor. So if it comes in as liquid, that's not much energy wise. You know, if it comes in, it's, you know, maybe 30, 40, 50 BTUs a pound, and it's leaving at 1,000 BTUs a pound, that's a pretty good energy loss. So moisture in the fuel represents an energy loss because it's going to go up the stack in the vapor form. I mean, unless, you know, in industry, we have what we call condensing economizers and things like that, but they don't put those on power plants that I'm aware of. Okay, heat in atomizing steam is considered a loss. Carbon monoxide. If you're burning your carbon to CO instead of CO2, that's a big energy penalty. What CO's got a heating value of I don't know, 3,500 BTUs a pound, where CO2 has no heating value. So, you know, you didn't get all the energy out of the carbon by combusting it. Yes, sir.
Why is heat and atomizing steam a loss in the credit?
I don't really know on the top of my head. You know, if we want to know, and we might, well, we could go back and dig around in the equations, but I'm telling you, it takes a while. But to answer that, I would have to go back and look in the equations and see exactly what they're calculating. I thought that when I read it too. I said, somebody's going to ask that. I'm going to get bagged here. Good job. Let's see. Well, any unburned fuel would obviously be a loss. So unburned hydrogen that makes it through the system up the stack, unburned hydrocarbons, certainly, just like the unburned carbon in the refuse, all that. Radiation and convection, that's from the outside shell of the boiler, radiation, you know, just well, when we went to Kingston, they didn't have a boiler operating, but if you go in there like in the summertime, it's hot. It's just around the boiler, it's probably going to be 90 to 95, 100 degrees. And if you go up on top to the top floor, it's more likely to be 110 to 120. They won't let you stay up on top very long because it's just too warm. So that's just the shell loss from the boiler. Radiation to ash pit. So this L sub P is kind of a hodgepodge here. So radiation to the ash pit, which is down on the bottom, you got water laying down there, and I guess that radiation heats up that water. And the theory is you're going to circulate water through that ash pit, and so you're going to carry some heat out with it. Sensible heat in slag and latent heat effusion of slag. So that slag falls off the walls, you know. One example, they were talking at TVA about there was a piece of slag the size of a school bus that fell down and took the bottom out of the boiler or something. So that's a little extreme. They also talked about going in with shotguns when the boiler was down and trying to shoot that stuff off the walls. I bet those good old boys have a good time doing that. They probably go in there and have competitions to see who can shoot the most slag off the boiler walls. And so, you know, there's latent heat because that stuff may come down liquid and then it congeals. So there's a phase change to a solid. So that's latent heat. And then the sensible heat as that solid cools down. So, I mean, it's amazing how detailed some of this stuff is. Sensible heat in the flue dust. So, you know, you got your precipitator, your bag house. When it captures that dust, it's hot. And so then it falls out of the system, takes energy, takes sensible heat with it. Excuse me. Heat in pulverizer rejects. So I think I mentioned this last time. The pulverizers, you know, they're these kind of old bowl-like devices, and they got a plunger that's, I don't know, probably 3 foot diameter, and that thing spins around and it pins the coal up against the side of the wall as it goes around in a circle and crushes it. And occasionally you get a rock or, you know, some inorganic material comes out of the coal, and they're designed so that stuff can fall to the bottom and come out. And so they call those pulverizer rejects, basically rocks and stuff that get into the pulverizer that fall out. And of course, I got 4-degree air being supplied up into those pulverizers to transport the coal particles into the burners. And so those things get hot and then they fall out and they take sensible energy with them. Heat and cooling water, you know, you may have pumps up in that control volume, other things that we had several on the diagram we went over last time, several different components that had cooling water flows to it. So the heat that comes out in that cooling water represents a loss. And then soot blowing, you know, we have soot blowers, and they will typically blow either low pressure steam or high pressure feed water. Water will tap off and they'll blow it, and then it leaves the system. So that represents a loss as well. And like I said here, we can pull down. I'm like, well, we could look for this, what this loss of atomizing. Where's the atomizing? I can't. There, L sub Z. I don't know. These guys are, and there's forms and all kinds of stuff down here. So this is where you get down where you're like there's L sub H, and it gives you an equation, and then, you know, you have to go run down all of these different variables. And I was just going to say, I don't know if I saw L sub Z, I might look at that. LMA, heat loss due to atomizing steam. So it's just, I guess, it's an enthalpy difference times WZ. So BTU loss per pound of ash-fired fuel. These are mass flows. I think that's the mass flow of fuel. I'm not sure what this one is. So then you just got to go. So like this, okay, just for example, this HRV, that's the enthalpy of saturated water vapor at TRA. That's the reference temperature. So when you do these tests, you have to establish a reference temperature. I usually pick like 70 degrees or 80 degrees or something like that. You just have a lot of calculations are based on the reference temperature. And so you just pick a reference temperature. I don't know that there's any real significance. I mean, you would want to pick a reasonable reference temperature. This is like for air coming in and stuff like that. So you pick a reasonable reference temperature, and then a lot of these variables are evaluated at that reference temperature. So for example, this H sub RV, etc. Okay, I think that's enough of this. I think you get the picture. Okay, so let me talk a little bit about the rest of the course. So this really finishes the formal material that I usually cover in this class. And of course, I'm just chagrined that I'm not to the end of the semester yet. I'm always run over, and I'm scrambling to get all this in, but I think it's probably a function of talking to the computer screen and not having 30 people in the classroom where we have discussions, and it speeds up. I just run through the material, and so we go through faster. I think it's probably pretty common. That said, I'm not quite ready to throw in the towel yet. I'm close. So what we're going to do is I picked a couple of topics, and probably the rest of this class, or at least most of it, we're going to talk about fracking. And instead of me talking about fracking, yes, I'm going to pull up some videos because those people know a whole lot more about fracking than I do. But I do have a couple articles that I will send you out. They're pretty darn good. I've used in the past. And so when I send out the link to this, I'll send out a couple of articles. And then I'll send out the links to, I've got a short fracking video that just about 6 minutes. It just says what it is. And then I've got a longer one that talks about the evolution of the procedure and in Texas. And it's pretty interesting, I thought. So we'll see. We may not do all of it, but I'll send you the links to it. And then next time, we're gonna look at some stuff on carbon capture and sequestration, which I think is a pretty big topic going forward. So I found some videos, and I'll see if I can find some PDFs or something that I can email out to you. I don't know. I don't have those yet, but I'll be looking for them. Okay. So that'll be Thursday, and then we won't have class next week. I'm not going to just keep, ginning up too much. I don't know. I might send you a link or two. If I can think of another topic or two that I find something that I think is really relevant, I may send you a link to watch on your own. Now, as far as exam is concerned, you're going to have a take-home portion, which is a combustion problem. And I will email that out Thursday or Friday of this week. You need to get it back to me, probably by a week, something like that. In the next week, maybe Saturday, something like that. So I can have a little bit of time to look at it. It's just one good sized problem. So I don't think it'll take you. It pretty well follows what we did in class on that example problem. So it's pretty much parrots that back. So if you understood that and followed along, I don't think you'll have any trouble at all with the take-home portion. And then we will have an in-class iLearn final. I will ask a few questions about fracking. I will ask some out of the carbon sequestration to give you some interest in watching that. And then we still have 2 STEAM chapters. We have the SOx chapter and we have a CO2 chapter. And so I will include those quizzes on the final. So between now and final, you'll have an Excel sheet to do on the combustion problem. I want it in Excel. And then on the final, you'll have a few questions on fracking, a few questions on carbon capture sequestration out of the videos on Thursday, and the SOx chapter and the CO2 chapter out of the STEAM book. And I think I've sent those out, but I can send all that stuff out again just to make sure that everybody has a copy. That will be on iLearn, and it will be the true false, the multiple choice. typical stuff on iLearn. Okay, so it gives you a little bit something to work on at home that just will take you back through those combustion principles, and then we'll finish up with the iLearn quiz. And then you guys are supposed to be sending me your presentation files, so get those to me as soon, ASAP. But I understand everybody's busy this time of year. Okay, are there any questions before I pop to these videos? I think that's about as much as I know about it right now. Okay.
Yeah, I was just gonna say, you said you were gonna send out the SOX and CO2 chapter.
I think I already have, but yes, I'll be glad to send those again.
Okay, great. I'm not able to find them at the moment.
Okay, well, I know, tech email does some wonderfully creative things with emails that sit on your account a while. I have things disappear all the time that I know used to be there. So I understand. I'll just be sure and send out everything that is going to be covered on the final to make sure that you have it. But be looking for that test. It's just one problem, and you'll get it either Thursday or Friday. Okay. Oh my gosh, we're up a little bit here. Okay, so let's look at. This fracking is really interesting. It's really kind of changed. It's changed the world, at least short term, and to see how long it lasts. Okay, so this is what is this? 6 minutes. We'll do this, and then we'll go to another one here.
For just 60 videos as you want, and you never need to pick up a camera or use any fancy editing software. Deep underground lie stores of once inaccessible natural gas. This gas was likely formed over millions of years as layers of decaying organisms were exposed to intense heat and pressure under the Earth's crust. There's a technology called hydraulic fracturing, or fracking, that can extract this natural gas, potentially powering us for decades to come. So how does fracking work, and why is it a source of such heated controversy? A fracking site can be anywhere with natural gas, from a remote desert to several hundred feet from your backyard. It starts out with a long vertical hole, known as a wellbore, drilled down through layers of sediment. When the well reaches 2,500 to 3,000 meters, it's at its kickoff point, where it can begin the process of horizontal drilling. It turns 90 degrees and extends horizontally for about 1.5 kilometers through a compressed black layer called the shale rock formation. A specialized perforating gun is then lowered and fired, creating a series of small inch-long holes that burst through the well's casing into the rock layer. About 3 to 4 months after the initial drilling, the well is ready for fracking to begin. Fracking fluid is pumped down into the well at a pressure so high it cracks the shale rock, creating fractures through which the trapped gas and oil can escape. The fluid itself is more than 90% water. The rest is made up of concentrated chemical additives. These vary depending on the specific characteristics of the fracking site, but usually fall into 3 categories. Acids for clearing debris and dissolving minerals, friction-reducing compounds to create a slippery form of water known as slick water, and disinfectant to prevent bacteria growth. Sand or clay is also mixed into the water to prop open the fissures so the gas and oil can keep leaking out even after the pressure is released. It's estimated that all of fracking's intense pumping and flushing uses an average of 3 to 6 million gallons of water per well. That's actually not a lot compared to agriculture, power plants, or even golf course maintenance, but it can have a notable impact on local water supply. And disposing of used fracking water is also an issue. Along with the trapped gas that's pumped up to the surface, millions of gallons of flowback liquid come gushing up. This liquid, containing contaminants like radioactive material, salts, heavy metals, and hydrocarbons, needs to be stored and disposed of. That's usually done in pits on site, in deep wells, or off-site at water treatment facilities. Another option is to recycle the flowback liquid, but the recycling process can actually increase levels of contamination since the water wells are typically encased in steel and cement to prevent contaminants from leaking into groundwater. But any negligence or fracking-related accidents can have devastating effects. Fracturing directly into underground water, hazardous underground seepage and leakage, and inadequate treatment and disposal of highly toxic wastewater can potentially contaminate drinking water around a fracking site. There's also concern about the threat of earthquakes and damaged infrastructure from pressure and wastewater injection. Links between fracking and increased seismic activity leave unresolved questions about long-term pressure imbalances that might be happening deep beneath our feet. Fracking's biggest controversy, though, is happening above the ground. The general consensus is that burning natural gas is better for the environment than burning coal, since the gas collected from fracking emits only half the carbon dioxide as coal per unit of energy. The pollution caused by the fracking itself, though, isn't negligible. Methane that leaks out during the drilling and pumping process is many times more potent than carbon dioxide as a greenhouse gas. Some scientists argue that methane eventually dissipates, so has a relatively low long-term impact. But a greater question hangs in the air. Does fracking take time, money, and research away from the development of cleaner, renewable energy sources? Natural gas is non-renewable, and the short-run economic interests supporting fracking may fall short in the face of global climate change. Experts are still examining fracking's overarching effects. Although modern fracking has been around since the 1940s, it's boomed in the last few decades as other sources of natural gas decrease, the costs of non-renewable energies rise, and cutting-edge technologies make it so accessible. But many countries and regions have already banned fracking in response to environmental concerns. It's undeniable that fracking has reshaped the energy landscape of the world. But for what long-term benefit and at what cost?
Okay. So, I'll make a couple comments, and anybody out there is certainly welcome to comment as well. Let's see, as far as the earthquakes are concerned, I saw a statistic, they've done a lot of fracking in Oklahoma, and something like the number of tremors recorded had gone from something like, I don't know, 10 or 15 a year up to 2,000 to 3,000 a year with all this advent of fracking, but they weren't very severe. The ones that, at least this report I heard, were not really causing, I mean, it wasn't like a big earthquake that was shaking things down. Now, whether it was causing, very small amounts of damage that really weren't going reported or recognized, I don't know. But I would hesitate to say that they weren't causing any damage, but it wasn't like that they were, every once in a while in Brookville, there'll be a little tremor or something. Or I lived in Memphis for a while, and it's on the New Madrid Fault, and we get little tremors in Memphis occasionally, 3-4 times a year, where a lot of times you wouldn't even feel them, but sometimes if you were standing in the right place, all of a sudden you'd feel this little shake going on, and then you'd hear on the news that there'd been a little tremor. Of course, Memphis is scared to death that there's going to be a huge earthquake. Because, Reelfoot Lake, I don't know if you know the story, Reelfoot Lake, which is up in Dyersburg, outside Dyersburg, Tennessee, was created by a huge earthquake back in like the 1870s. I think it was I may have the dates wrong, I probably do, but it was such a severe earthquake that the Mississippi River flowed backwards for a number of hours, and it created this Reelfoot Lake, which is a great little fish lake. But anyway, so, you know, earthquakes, natural earthquakes do happen, especially in that end of the state. So, you know, the earthquake thing I think is real now, how serious it is, because I'm not aware that there's ever been a serious earthquake that had been kind of tied to fracking, but there have been many, many small, you know, tremors in the ground. On the wastewater contamination, what I recall hearing is that's happened maybe once or twice, that's not a common occurrence. You could check, somebody get out there and Google me, you know, sometime and see if there's more occurrences. But as far as I know, that's been a claim. Don't think it has come to fruition, hardly at all, you know, maybe once or twice, and I'm not sure about that. Okay, anybody else have any comments? See, this is why we get through the material so fast. That's okay. All right, so this is a longer one. I started listening to this. I thought history lesson a little bit.
This life-saving device stops a person from choking in seconds. Do you know what?
Yeah, you can see where I was watching.
In recent years, a silent revolution has taken place. We thought the age of fossil fuels was coming to an end, and we hoped we were heading for a future filled with renewable energy. In Texas, the old oil industry, a handful of men have caused a dramatic shift, putting the United States firmly back on the map as an oil and gas producing superpower.
This breakthrough on shale turned out to be the biggest energy innovation so far of the 21st century.
Thanks to the shale revolution, and with President Trump at the helm, the United States is straight for total energy independence.
President Trump will fuel America's future and become the energy independence.
The shale revolution has opened up a huge reservoir of fossil energy.
I'll say this, wherever there's oil fields, there's shales somewhere nearby that have not been drilled. And that's all over the world.
But what exactly does the shale revolution entail?
We shouldn't be exploiting any more fossil fuel gas because it's ruining our planet.
This is Backlight. Welcome to Trumpland.
Can I have everybody's attention?
The whole world is keeping close tabs on the states, where a few men in Texas are turning the energy supply industry on its head.
Can I have everyone's attention? It might be worth saying a few things about what Mitchell and how it has impacted the world.
Dan Stewart was a team leader with Mitchell Energy, a small gas company that unleashed the shale revolution in the late 1990s. Once a year, the team gets together to celebrate their success at extracting gas from the Barnett Shale rock formation in northern Texas.
Mitchell started the Barnett looking for something to save the company because we knew that our shallow reserves were decreasing, and if we didn't have something to replace it, we were not going to keep building reserves.
Over half the oil that has been produced in the whole world was produced in the United States, mainly in the states of Texas, California.
It looked as if the heyday of the US as an energy-producing superpower had come to an end. In the previous few decades, America had become known chiefly as the biggest consumer of fossil energy.
America is addicted to oil.
The country had become more and more dependent on foreign oil and gas. On several occasions, this led to costly and radical military intervention, the consequences of which are still to be seen.
If we hadn't proven the Barnett when we did, the price of natural gas would have gotten up to probably $20 an MCF and would have destroyed our economy.
The production of oil and gas in the US was dropping fast. George Mitchell was one of the many who needed to rescue their business. He had to find a new way of extracting gas and believed shale could be the way to go.
So what Mitchell started turned into a world-changing supply of energy. And in my opinion, it was a gift from God.
Deep below the face of this barren land in northern Texas lies the Barnett Shale rock formation.
We're going to visit a landowner and see the CW Slay #1, which was the first Barnett well that was ever fracked. And the landowner here is we're going to meet.
In the late 1990s, Nick Steinsberger worked for Mitchell Energy as an engineer. It was he who discovered the crucial technique for extracting large volumes of gas from the shale.
This sign with the Devon Energy sticker over the top of it is the old Mitchell Energy sign. You can see it basically with the words here, Mitchell Energy Company. This sign is the CW Slay #2, which was one of the first wells drilled in this area. And the symbol of Mitchell Energy at the time was the mountains and the sun, which signified energy for both the sun and mountains.
Thanks to this so-called slick water fracking technique developed by Nick, this arid land became a gold mine.
So I wanted to introduce you to a friend of mine. Carl Smith is a friend of mine and a landowner in the Barnett Shale, and he's had some wells drilled on his property.
How did it start when you, the company approaches you, or what?
Yes, an agent from a company such as Devon or Exxon, whoever it is, will approach a mineral owner like myself, and then you negotiate a contract. They'll pay you per acre on your land, so much per acre to lease it. And then when they come out and make a location, they pay you damages. And also you negotiate on how much percentage you get from 20 to 25% of the revenue that the well produces.
And in your situation, how the
25%, yes. Mm.
So you got 25% of
the sale of oil and gas off of that well.
So all proceeds, he gets 25% of all proceeds from the production of each well.
Before operation costs. Mm-hmm. You get yours off the top.
It sounds like a lot. I'm not an expert, but
it could be a whole lot. Yeah. Some people got very wealthy. I didn't happen to be one of them, but some of them made lots and lots of money.
Now I'd like to keep the oil around just so I can remember what it is I'm in the business for. Smell. I love the smell of crude oil. You don't want to spend a lot of time smelling that, but it smells very sweet.
Kent Bowker was the first to discover that the Barnett Shale formation contained an astonishing amount of gas.
This is the area where I thought Mitchell Energy should go in and start leasing land in anticipation of this becoming a huge oil and gas field. You can even see where I said where we should probably drill our first well. We drilled the well. We brought the rock up to the surface. I have a piece of it right here. This is a piece of Barnett Shale. We drill it, we bring it up to the surface. And when we bring this up to the surface, it was just bubbling, huge volumes of gas. And I looked at it, and I put some soapy water on it, and it just bubbles. And where's all that gas coming from? I mean, there's no holes in this that I can see, but there has to be holes because the gas has to be coming from someplace. So where? So that's where I thought, I need to understand this rock. I need to understand where's the gas coming from and how much is in there, because there's a lot more gas than people realize.
So far, the oil and gas industry had regarded shale as unexploitable. The rock was too hard and too impenetrable to extract gas from it in sufficient amounts. But Nick came up with a fracking technique that would change all that.
The shales are so tight, the rock is so dense that when you drill into them, the hydrocarbons or the oil or the gas will not come out of them until they are fracture stimulated. Okay, so what I have here is a wellbore. This is one string of casing to protect the surface groundwater and cement it up to the surface. And here's another string of casing, which is our producing casing. And then we pump fluid down the wellbore and through those holes into the reservoir. And then when it goes through the reservoir, it creates lots of fractures in that reservoir. And that's what the gas molecules come through those fractures into the wellbore and back up, and it flows back up to the surface.
And this is the shale.
So the shale would be right here.
Yeah. And the shale was actually considered like worthless by
all of industry. So even Mitchell Energy and others would drill down through the Barnett looking for other potential zones, and they'd always see oil and gas from the Barnett, but they knew it was the source rock, and it was going to be hard to extract those hydrocarbons from the Barnett itself. And so they were looking more conventional plays where they could more easily be produced.
People thought we were absolutely nuts. We were crazy. One of my good friends at Mitchell said, Dan, I don't know what y'all are doing, but all this is just smoke and mirrors.
I think that what everybody had learned in school and what everybody had learned from experience is that shale could not work.
Daniel Yergin was a professor at Harvard. These days, he's a consultant for the international oil and gas industry.
In that period of starting around 1998 into the first couple of years of the 21st century, they broke the code and liberated shale.
This is the CW Slay #1, and this was the first well that was fracture stimulated in the Barnett Shale. And this is a wellhead so that the gas comes up and it goes underneath the ground to back by my car over here, which is the separator and the production tanks. So 16 years ago, I fracked this well with a slick water frac. And then after that, this well has been sitting like this basically for the last many, many years. So without any noise, without any interference, and it's just been sitting here producing for a very long time.
I came to work at Mitchell at a time when Nick was figuring out how to decrease the cost of the stimulations of the frac jobs. So when I showed up, I said, hey, there's 4 times more gas here than you guys know. And then Nick's figuring out a way to be able to stimulate the wells and drill the wells for half the cost. So we have 4 times the gas, we have half the cost. All of a sudden a miracle occurs, and then George Mitchell, he got the biggest smile on his face, leaned into the table, looked at us all. This is huge. This is the biggest secret the company has ever had. No one can talk about this. He knew what it meant when we told him how much gas was in the Barnett. He let loose the land teams. They went out and leased land all over the place, areas that never had produced oil and gas in Texas. All of a sudden, we're starting to see drill rigs, starting to see landmen, starting to see Mitchell come and drill wells. Because of the work and the discoveries we've made in the Barnett, the field grew and grew and grew, got much bigger than we even thought at Mitchell, and became eventually the largest onshore gas field in the United States.
I think when the shale revolution, even when it got going, if you had predicted the scale, the impact, and the rapidity with which it happened, you might have been committed to an insane asylum. People would just have said, this is not possible that it happened. So I think everybody who was involved and made it happen could not imagine, once it got going, once this kind of entrepreneurial industry sort of assimilated how to do it, how fast it would happen, and it would not just end up being in Texas, it'd be in other parts of the country and other parts of North America, including Canada. And now people, for instance, think the Marcellus region in Pennsylvania and the east part of the United States may be really the second largest gas field in the world.
It looks as though fracking heralds a golden future for the American energy market. But there are major differences of opinion about the safety of the technique. It is said to pose several dangers to the environment, to cause earthquakes, and to contaminate the underground freshwater reserves.
Do you understand the opposition right now to your work?
Frankly, they get upset. They want to know it's disruptive. It's going to pollute the environment. Everything we do pollutes the environment to some extent. But if we want cheap, reliable, clean burning fuel, natural gas is the way to go. And it's not nearly as bad as what people think.
They fear that we're going to cause earthquakes. They're going to fear that we're going to contaminate the groundwater, and rightly so. But there's been hundreds of thousands of wells drilled and fracked in America, and very, very few instances of water contamination. All in all, I believe that the benefits far outweigh the risks.
One of the unique things we have here is we have shale core stored here from lots and lots of wells throughout the nation. What we try to do is keep it kind of a secret because it's very, very valuable. Companies spend millions of dollars to get the secrets of the shales out of the ground.
Geologist Ken Morgan manages the treasure chamber of the shale industry in a secret location somewhere in Dallas. Here at this laboratory, shale rocks from all over the United States are stored for research.
In this room is millions of dollars of rock, stacks and stacks of shale core, all in boxes for observation and research. And now we're in our shale core viewing lab. What we have here is rock core, or tubes of rocks that have been pulled out of the earth by the oil and gas companies. And we can see, we just unwrap these and the companies come in and look at these. They can spend as much time as they want to in here. And their purpose is to try to figure out where to drill. Top of the formation or the bottom of the formation? Maybe in the middle, but where is the hydrocarbons that they're after? If you take a look at this one, notice the big change that occurs right here. Above there, right there, is high organics, high oil and gas potential. Below that line, look how it changes. Much less carbon, much less hydrocarbon stored in the rock. So guess what? A geologist will see these changes and suggest to the company, stay in this part of the rock. This part will not produce the oil and gas we're looking for. So it's very critical about what rocks to drill into. You may have a drilling program that is $50 million, $500 million of drilling operation. So this core may guide a tremendous amount of money that's going to be used for drilling operations.
Do you know any people that got very wealthy thanks to?
Oh, yeah, yeah.
Yeah. There was a ranch down in South Texas called the Harrison Ranch that Shell leased it for $1 billion, just the lease. It was $1 billion. It was over 100,000 acres, and they paid him $1 billion just for the opportunity to drill on their property, and then plus they shared in the revenue stream after that. So,
Well, to put it in perspective, the ranch itself was not worth near $1 billion. not, I mean,
Oh, yeah.
maybe 8 million, $10 million at the most. So to get $1 billion just to drill on it, plus the revenue, just made people rich.
I think that's one of the biggest reasons why the shale revolution was so successful in the States, whereas I'm not sure as how successful it will be other places, because the landowners like Carl share in that wealth and if they make money, they're happy, and the oil and gas companies are happy if they make money too. So it's a shared experience, where in other countries that they don't own the minerals, they're not as happy about oil and gas companies coming onto their property and drilling and exploiting their minerals and land.
Shale has grown into an industry worth billions. The new generation of young entrepreneurs is barely interested in conventional oil and gas anymore.
Scott, you mind if we borrow you for a second? This is, we'll let our controller out. I'll go back to the corner. This is our head of reservoir engineering. This is Scotty. You want to show him where the Barnett Shale is, Scott?
This is the Barnett in North Texas. This is the Midland Basin, Delaware Basin. That's very, very attractive right now. This is the Eagle Ford, and then this is East Texas and the Haynesville Shale.
And these guys, the names, like
they're just, you know, they were the guys in the 40s and 50s that pioneered a lot of the oil and gas companies in town.
And perhaps in the future they have a different map with
Matt's face on it, not mine. So it's the trick is making money. That's the real trick.
The big bucks are now to be made in shale.
This is Adam Griffin.
Nice.
He's our head of land, our vice president of land.
Nice to meet you guys.
Matt Miller is one of the modern oil and gas entrepreneurs. He runs an investment company in downtown Dallas that focuses exclusively on shale.
I think that shale has decreased the risk of finding oil and gas per well. You know, if you think of, oversimplifying here, but if you think of conventional oil and gas as there's a bubble of oil in the ground, I'm going to stick a straw in and try to pop that bubble. Whereas unconventional or shale gas is, I'm going to drill down into tight rock, I'm going to fracture that rock, and that'll allow those hydrocarbons to flow out of that rock and up the wellbore. What that's done is it's made a much lower risk profile to find oil and gas. It's made dry holes something of a past for the industry. It tends to be a lower risk proposition. There's more capital going into shale. Usually whenever there's more capital, that means that there's more jobs that are associated with shale exploration. Therefore, there's more opportunity as a young person to get one of those entry-level jobs. Yeah. That tends to be the cycle that we're seeing right now. So it creates hundreds of thousands of jobs. It's a very, very capital-intensive industry.
And how about the revenue?
We hope it's revenue intensive as well.
The impact of the shale revolution has really been enormous, not only for the U.S. energy industry, but for the U.S. economy. We had at our conference in Houston in early 2014, Ben Bernanke, who had been the chairman of the Federal Reserve, he just stepped down. And I said to him, what's the impact of this shale revolution on the overall economy? And he said, it's one of the most positive things that's happened to our economy since the financial collapse of 2008. Then he paused and said, maybe the most positive. So it had many positive effects that just were not anticipated. In the case of gas, and then in the case of oil, once it started unfolding, it unfolded a lot faster than people thought and turned out to be a lot bigger.
Basically, after Mitchell and other companies learned what to do with these gas shales and these tight gas sands and limestones, then people started looking at oil and saying, well, you know, we think we can apply this same understanding and technology to some of these rocks out there that have oil in them. And pretty soon, we are very close to surpassing our previous peak oil.
The US supply just kept increasing at a faster and faster rate. And you had a world oil market that was oversupplied. And in November of 2014, OPEC, really led by the Saudis, just decided that if they cut back, all they were going to do was keep prices high and make more room for the United States, make more room for Russia, make more room for other countries. And they said, we're not going to do that anymore. And then the price began to collapse, and it collapsed a lot more than people thought.
We glutted the gas market first, then we glutted the oil market to the point that we interfered with OPEC's profits. When we interfered with OPEC's profits, they said, well, we got to shut this down. We were taking away some of their customers. So they decided they had to basically go to war with US operators for survival's sake. And so they started pumping out a lot more oil and dropping the price.
The idea was shale production, oil shale or shale oil production is very expensive. US producers will not be able to drill any wells at these prices. Production declines very quickly out of these fields. And therefore, all we have to do is wait around a couple years. We can outlast the US producers. They're gonna suffer. Prices then will come back up because US shale production will drop, and it didn't happen.
For the industry, there's a pro and there's a con, okay? The con is, yes, a lot of people lost jobs, and I hate that. I hate that. A lot of companies went bankrupt. I hate that. But our country gained from this because the companies that didn't go out of business figured out cheaper ways to get more reserves in order to combat the lower OPEC price. And that's the problem. Once the cat was out of the bag, once we figured out that we could get this oil and gas out, then it's just a matter of how do you get it out better.
The price war started by OPEC caused a survival of the fittest scenario. Only the shale producers who learned to extract more efficiently and more cheaply using innovative techniques managed to survive. They became the heroes of the industry.
This is Trinidad rig number 433. We are in West Texas in Midland County. This is drilling a vertical Wolfberry well to 11,400 feet. We are on day number 7 right now, and they're 9,000 foot deep. We're going to be going to 11,500 foot deep.
And you're drilling into shale rock formation?
We are drilling into shale, and it's shale, sandstone, and carbon. It's 3 separate types of rocks. These wells typically take about 9 days to drill. We can move this entire operation in 12 hours, and so they'll be moving in 3 days approximately. When we go to move, we will tear all of this down, move it to another location, and rig everything up and start drilling the next well. That entire operation takes about 12 hours. It's extremely efficient how quickly we can tear this down and move it. When we move the drilling rig off, then a crew will come on and fracture the well, and that's going to take about 3 days. And after the frac crew leaves, we'll put a pumping unit on the well, and we'll start flowing oil and gas.
Fasken Oil and Ranch, based in Western Texas, survived the price war and is now one of the leading shale producers. Thanks to innovation, they are currently getting oil out of the ground at a much lower price.
When we first started drilling these wells back in 2008, they were 20 to 22 days, okay? And then when we did the partnership with Trinidad, we first started drilling in 14 days. And then as Corey come on and the bit technology got better and the motor technology and these hands got better and more efficient, we've gotten them down to 8 days sometimes. That is phenomenal. And it has to do with the technology.
I think that OPEC's strategy is a failing one in that OPEC underestimated the resilience of United States oil and gas producers to get oil and gas out of the ground at a lower cost. And I think they also underestimated the efficiency of the US capital system. One of the things that benefited our industry greatly is the ability to restructure debt very quickly. About $66 billion of E&P firms went bankrupt. About 85% of those dollars restructured. The companies didn't liquidate, the companies didn't evaporate. They emerged with a different structure to their balance sheet. So the oil and gas still comes out of the ground, but you don't owe the bank money, you just own a restructured entity. So the US bankruptcy code allowed us to fight the OPEC fight in a much more efficient way over the years.
OPEC is an organization of 14 oil exporting countries. It is often regarded as a cartel because it can influence prices by increasing or decreasing the oil supply. For many decades, OPEC dominated the oil market, but it looks like the shale revolution will put an end to that.
The agreement that OPEC reduces approximately 1.2 million barrels a day to bring its ceiling to 32.5 million barrels per day, effective 1st of January 2017. Thank you very much for coming.
After 2 years of trying to push the shale producers out of the market, OPEC threw in the towel last November. The cartel decided to reduce production in order to get the oil price up again.
When the price got really low, the OPEC countries were really hurting because they need $50 a barrel or $60 a barrel to support their countries. They're going in debt supporting their countries at prices lower than that. Where a low price for us, it hurts the oil companies, but as a country, we're still doing fine. We have all kinds of other industries, right? So that's the difference. What happened is that we just outlasted Saudi Arabia. They can't take the pain anymore of their debt. And so they've decided to cut production. And so now the price comes up to 50. I think all the companies in the Permian Basin can make good money at $50 oil.
Yeah, if you think about the break-even price for shale on a just a blended basis across the United States, prior to the collapse, you might have thought about it as being $80 per barrel. Post-collapse, again, well cost to drill go down. Post-collapse, that break-even cost is around $55 a barrel. If I'm OPEC, I've repriced my barrels in the ground from $80 to $55, really without harming the United States oil and gas industry all that much. I don't think it was a good strategy.
It's gotten cheaper. We're getting more oil out of the wells for less cost. And so that's where we're at. 10 years from now, I don't know. Maybe we'll be able to produce it at $30 a barrel. Everybody in the U.S. It just depends on how much we can recover and how good we get at that recovery. But it's a tremendous thing for the United States of America to have this play. It's changed the whole political structure of the world. What's happening right here.
The addition of U.S. shale has certainly shifted away from an OPEC-dominated world oil market to a much more competitive oil market. And that's been driven by this amazing increase in U.S. production. I think it's now recognized that it's part of the mix. I think it's also recognized that it's not high-cost oil. It's medium-cost oil. And there are other oil supplies that are higher cost around the world. And so it's a recognition that shale is going to be part of the mix. It's not going away.
Now, one of the big questions we have about who would want to come and visit here. well, from all over the world, from China, Japan, South America, Middle East, all over Europe. You name the country in the last 3 years, they visited in here to see what this is all about. And do they have the potential for it? I'll say this, wherever there's oil fields, there's shales somewhere nearby that have not been drilled. And that's all over the world. So we see a really big future for shale being able to deliver oil and gas. So all the Middle East oil fields are conventional sands and limestones that produce oil. Guess what's underneath those gigantic oil fields in Saudi Arabia? Shales that have never been drilled, that are untapped, that will be decades and decades of potential production into the future.
Shale gas and oil has introduced even more fossil fuels onto our energy market. This abundance of cheap fossil fuels now threatens to price renewable energy out of the market. Many people wonder how it will affect our efforts towards a sustainable future.
What in the United States, what low-cost gas has done is really pushed coal and taken market share away from coal. Coal used to be more than 50% of electric generation not so long ago. Now it's under 30%, and gas actually has a bigger share. So, I think there's a long-term energy transition happening. I think it's going to unfold over many decades, not over many years, but renewables will become progressively more important. I think natural gas plays a particularly important role as a partner of renewables because renewables are intermittent. The classic thing is the sun doesn't shine all the time, the wind doesn't blow all the time, and so gas is an important part of the mix.
Shale gas as the ideal partner for renewable energy. That's one way of looking at it, according to the Americans. And as they now have an abundance of gas, thanks to the shale revolution, they present themselves as the new energy superpower on the world stage.
This facility started with the idea that the US was going to be short of gas. And so the decision was made to build an import facility. So we built the import facility. It was started up in 2008, 2009, right when the shale revolution started. And so since then, the facility hadn't operated. As the shale revolution kicked off in 2010, we actually announced that we were going to export gas. And so we undertook building the export facility that you see behind me.
So this actually was a facility to import gas to the United States.
Correct. And now what we've done is we've turned it around to export gas to the rest of the world from the United States.
In terms of oil, it's very similar that the U.S. in just a period of a little more than half a decade almost doubled its oil production. And people started saying that the U.S. was going to overtake Russia and Saudi Arabia to be the largest producer of oil in the world. And now when you think of world oil, you have to think of the big three: Saudi Arabia, Russia, and the United States.
Our cargoes have been exported all over the world: South America, Southeast Asia, Europe, the Middle East.
How come the Middle East needs to use shale gas?
They're actually building import terminals in several countries in the Middle East. And so, our production and our price matches up with their needs.
But isn't it ironic that the U.S. is exporting gas to the Middle East?
Yes, it is actually. This month, the U.S. has actually become a net exporter of energy due to the fact that we've had the shale revolution and we're able to export LNG.
The first imports of U.S. oil from the Middle East was from Kuwait in around 1948. And now it's just a turnaround. The U.S. will actually be among the exporters of natural gas to Kuwait. And that, if you sort of think about it, it really shocks the mind.
what does this mean for the old school oil producers? The main oil exporting countries are increasingly worried about the United States as an energy superpower.
We're still seeing the unfolding geopolitical impact of the shale revolution. Middle East countries express concern that the U.S. will be less interested in the Middle East because it will be importing a lot less oil. And I think that there's a sense that this enhances the autonomy and the position of the U.S.
The fact that we are less dependent on foreign oil is great for the United States. You know, we were importing probably 60%, maybe a little more than that. Now we're only importing less than half. And we have the potential to further reduce that. And I don't know if the United States will be energy independent, but certainly North America could be energy independent with the Canadians and the Mexicans. That whole region, we could produce what we use.
I think the shale revolution and its impact on prices has not only hit the budgets of oil exporting countries, of petrostates, but has also hit the very conception of how these states work and their overdependence on oil revenues, and the fact that they set their budgets at high prices and expenditures and then they have to cut them. And I think what it's done is sent a very powerful message about diversifying economies and managing your oil revenues differently so you're not vulnerable to cycles. Because I think the oil exporting countries became accustomed to high prices and assumed the high prices would go on forever. And they based their budgets and spending on that. And then reality delivered a very powerful shock with which they're still dealing.
In Saudi Arabia, they have oil. That's their economy. And it supports their whole nation. In America, in the United States, we have lots of economies, okay? And they all support, so we're diversified. That's a good thing. That's a good thing for your country because now you have two sources for gas. So if you just have one, that guy's in total control, right? He's not in total control anymore. That's a good thing. That's a good thing for your country. You're not totally dependent on Putin now, right? If we can export to you, then he's going to try to come to the table and say, hey, I'm not going to really cut that gas off this winter like I did before, because I know you can get it from the US.
From Europe's point of view, to have competition between Russian gas and US natural gas, first of all, is valuable from an economic point of view because it means more competition. But it's also valuable because it gives diversification of resources, and that gives resilience to the energy system, particularly at a time when Europe's own gas, preeminently from Groningen among others, is going down. Europe's going to need to import more gas, and it's wise to import it from a number of different suppliers.
The gas reserves in the Netherlands are diminishing fast. Shale gas seemed a good solution, but it is met with a lot of resistance.
Ja, nou, het is net of ze het ons door de strot willen duwen. Dat gevoel heb ik er nu bij. Die bodemgesteldheid is hier geweldig en die laten we niet verpesten door een paar jaar van die schaliegasboringen hier toe te staan.
Ja, maar als we nu zeggen Groningen niet en we willen geen schaliegas en we willen Russisch gas niet en we willen Noordzeegas niet, waar moet ik het gas dan vandaan halen?
The Dutch government has decided to ban shale drilling for now. In the United Kingdom, however, they think it has great possibilities. Various companies are trying to convince people that it's the path to follow. Ineos is one of these British companies. They hired the Texan pioneers as consultants, hoping to copy America's success in the UK.
Beneath the surface of the United Kingdom lie huge shale gas deposits. The British government thinks this gas could transform UK industry, making the country energy independent and creating tens of thousands of new jobs in manufacturing.
British government wants to develop shale, not only because it needs additional natural gas, but also because it sees the economic benefits for its industry, for its competitiveness, for job creation. But it's run into a lot of environmental opposition. And so, not much has happened in the UK, despite the determination of the government to go ahead.
The locals firmly oppose the initiative. One of the main reasons being that fracking in the Texan prairies is in no way similar to fracking in a densely populated Europe.
Protest has been held in Sherwood Forest against plans to survey for shale gas. Exploration is at an early stage, still in negotiations, but there are fears in the long term it could see fracking of land under or adjacent to the ancient woodland.
They need to do the seismic surveys before they can find out where it's safe to frack. And we're saying it's not safe to frack in this area.
I'd prefer we were putting money into renewables.
We shouldn't be exploiting any more fossil fuel gas because it's ruining our planet.
The shale revolution threatens to revive the use of fossil energy. How will this affect all our efforts towards a future based on renewable energy?
Because of this abundance of gas and oil created by the shale revolution, now the incentive to invest in renewable energy will go away. How do you look at this?
I think it is a bridge fuel. I don't think we're going to be living off deriving energy from natural gas forever and ever. I think eventually we are going to reach a point where the technology is there, where renewables are economically viable.
We've seen in the last decade is the costs have gone down a lot and the scale has increased. And so renewables are clearly going to have a growing share of the energy mix in the years ahead. I think renewables have made a lot of progress and they'll continue to make progress.
Technology advances forward. It's going to eventually get to the point where the battery systems that we have, the transmission systems, the generation systems, either with solar or wind, get to the point where at a price point, they can compete with natural gas. And at that point, gas will fade away and renewables will come in. Never bet against technology. We're going to come up with better storage systems, better generation systems, just the same way technology started the shale revolution.
Ultimately, the lowest cost provider wins, and you need to be comfortable and agnostic about that. If wind or solar beats out a natural gas power plant, it doesn't matter how much government regulation or Trump helps or anything along those lines. You're going to lose. Economics wins.
The shale revolution has upset the balance of energy relations across the globe. If the political wind changes following Donald Trump and Brexit, many countries could soon be tempted by the potential economic benefits of shale exploitation.
Thank you for watching. For more on this subject, take a look at the playlist. You can also watch this recommended video. Don't forget to subscribe to our channel and we'll keep you updated on our documentaries.
Okay, guys. There's a few of you still out there. I figured I'd go ahead and let it run to completion here. So go ahead and stop the recording.